Thus far, we've been discussing the support vector machine under the assumption that the two classes are linearly separable. So what happens if they aren't, and this is going to be more likely the case? How can we modify the SVM in order to take into account the fact that some data points might of necessity fall on the wrong side of the separating hyperplane? So to handle this, we discuss something called the Soft Margin Svm. And the difference between the SVM as we've been discussing it thus far and the Soft Margin Svm is the introduction of this thing called the slack variable. So for every single data point where we have this original constraint that this had to be greater than or equal to 1, we now introduce a slack variable, psi I, that has to be positive or equal to 0. And then we allow some slack here. So we, for some data points, allow psi I to be greater than 1, in which case we allow for that particular point xi, we allow for it to be misclassified. So here's a picture of that to give some intuition. So here we have the separating hyperplane, and then for a particular point, for example this one, that falls on the wrong side of the hyperplane, we allow the slack variable to be greater than 1. So that accounts for the fact that we don't actually perfectly classify that point, that the sign of y and our linear classifier disagree. Whereas for a point, for example here, that falls on the correct side has a psi that's less than 1, and for some of these other points, psi would be equal to 0. So this is what we're looking to add to our SVM. So we therefore need to formalize this by building it into our objective function. So the way that this is done is that we take the original objective function, so we wanted to originally minimize this term, and now we add to it the sum of these slack variables, and because they have to be positive or equal to 0, that's a constraint that we add. This sum is going to be a positive number, and we pre-multiply that by some regularization parameter lambda that says how strictly we're going to enforce linear separability. And we also modify our constraint by subtracting psi I from the ith constraint in order to potentially allow the ith data point to be misclassified. And now we want to minimize the sum of these two terms. So we want to minimize the L2 norm squared of the regression hyperplane defined by W, and we want to minimize the sum of these slack variables. So we don't want to set too many greater than 0. We can quickly see the role of lambda in this setting. So for example, if lambda is extremely small, say in the limit as it goes to 0, then we're essentially paying no penalty for letting psi be greater than 0. And so we're really allowing anything to be misclassified. We can't really learn that in that way. When lambda gets bigger and bigger, as it goes, for example, to infinity, then we're paying an infinitely large penalty by letting any of these psi's be greater than 0. And then we get back to the original SVM where we're trying to enforce perfect separability. So lambda is this additional parameter now that we have to set. It's a number greater than 0, and it can be set in a few ways. The most common way would be to use something like a cross-validation type technique. The important thing about lambda is that it's going to change the hyperplane that we learn. For example, here's a case where lambda is very large, and so we learn this hyperplane, and these are the points that have their corresponding alphas greater than 0. And then for lambda very small, we would learn, for example, this hyperplane. So the takeaway from these slides is that the hyperplane is going to adjust itself based on what we set lambda to be. So let's look at how we can learn the soft margin SVM. Again, we have our primal problem where we have the sum of the two terms, which is a trade-off of the original thing that we wanted to minimize, plus a penalty on these slack terms that we're including, subject to these two constraints. So the original constraint, including the slack that we're now going to allow, as well as the constraint that the slack variables have to be non-negative. We again construct the dual by adding Lagrange multipliers. This time we're going to add a Lagrange multiplier alpha I to enforce this constraint, and another Lagrange multiplier, so this is new mu I, to enforce this constraint. And we have this dual problem that we now want to minimize over W and W naught and these slack variables, and maximize over the Lagrange multipliers. In this term, we have the original objective that we want to minimize. We add our Lagrange multipliers, so this is from before with the additional slack variable here. And then also minus the Lagrange multiplier time, the new Lagrange multiplier that we include to enforce and penalize the slack variable psi I. And this now we want to maximize over alpha I and mu I, subject to the Lagrange multipliers being non-negative, and also subject to this term now being non-negative, where we've introduced the slack, which allows us to violate the original non-negativity constraint. Okay, so now let's look at solving for the dual problem. We minimize L over W, W naught, and each psi I by taking the derivative and setting to 0. We get these two original constraints again by minimizing over W and W naught. So this is exactly as before, plus this additional constraint which comes from taking the derivative with respect to psi I. So from this, from minimizing over psi I actually disappears, and we're left with this constraint that lambda minus alpha I minus mu I has to equal 0. So now if we plug W back in, and I have a typo here, this term, if we solve for mu, gives us lambda minus alpha I. If we plug W back in, and we plug for mu I back into L, lambda minus alpha I, we'll find that we have the dual problem, which is equal to this. So actually, we have exactly the same maximization problem over alpha, subject to this constraint, which comes from this requirement here, plus an additional constraint that alpha I has to be greater than 0, which is as before, but now less than lambda, which is the new thing. And so this is all that's new with the SVM including slack variables, this lambda term here. That's the only difference. Now alpha I has to be less than lambda as well. So where do we get this? Well, alpha I and mu I are both positive or non-negative, and lambda is something we set, and we have this requirement that alpha I plus mu I has to equal lambda. So of course that means that if alpha I is greater than lambda, the only setting for mu I that we can have to make it equal to lambda would be a negative number, which violates the constraint on mu I. So by the fact that mu I has to be positive, that means that alpha I has to be less than lambda, because alpha I plus mu I has to equal lambda according to this constraint, which we get by minimizing L over psi. So this is the SVM where we've now introduced slack variables. We have this as the only difference. But we also now notice, what if we kernelize the SVM? So we, instead of working with X, we map X to a higher dimensional space. Then we end up with these dot products between these higher dimensional mappings, which we've already discussed can be replaced with any valid kernel that we want to define on X and xi and xj. So we can simply replace this dot product with a kernel function between the two data points, xi and xj. By swapping this out and swapping the kernel function in, we kernelize the SVM. So now we have a kernelized SVM with slack. That's the final SVM that is the most popular and the most versatile SVM. So how do we do classification? Exactly as before, we have that W now is equal to alpha I, yi times the mapping of xi if we want to do a higher dimensional mapping. And now sum over each I. So we've taken xi out and replaced it with its higher dimensional mapping. we get that W equals this. And just as we've discussed in previous lectures about kernels, when we make a prediction for Y naught, we're simply predicting the sign of the dot product of the mapping for the corresponding X naught with W plus W naught. And with this, from this mapping, we get that we can replace the dot product with the kernel, and that gives us the prediction. So we now predict based on the sign of this function here, plus W naught. So here's what we end up with on this data set that we've seen a few times before. The black line here corresponds to the decision boundary, which arises from this classification rule. So we've done the kernelized SVM, where we use the RBF kernel, Gaussian kernel. We make our predictions based on a sum over alpha I times yi times the kernel between our new input point X naught and all of the data points in our data set plus W naught. That'll give us something like this. And from the SVM algorithm, many of these alpha i's will be equal to 0. And for any alpha I that's equal to 0, we can interpret this as saying that we don't consider the I theta point in making our classification. So any data point for which alpha I is positive is going to be a data point that we use to classify. Those are called the support vectors. So the data points xi for which alpha I is positive, because we view these data points as vectors, they're called the support vectors. So for something like this, each of these black dots is placed over a data point that has alpha I non-zero. So for example, the alpha I corresponding to that data point is equal to 0, whereas the alpha I for that data point is greater than 0. So these are the data points that are actually going to be used, these black dots, in making our classification. After running the SVM, of course, all of these data points were used to learn the SVM, but after learning it, we could literally throw away any data that doesn't have a black dot over it. We only need to keep the data that has the black dot, and we only calculate the kernel between the new point and the points that have an alpha greater than 0. So that wraps up support vector machines. To summarize, with the basic SVM, we had a linear classifier assuming that the data was linearly separable. The position of the affine hyperplane was determined so that we could maximize the margin between the two classes. So that's what the SVM was doing for us. It was maximizing the margin between the two classes. The dual problem we set up to now maximize the dual. We didn't go into detail about this, but we can show that it's a convex problem, or it's a concave problem. We want to maximize it, so we have a convex optimization problem, meaning that whatever algorithm we have, when it converges, we get the solution to the problem. We find the values of alpha that maximize that objective function. The full-fledged SVM, which we discussed in the second last part of this lecture, includes maximum margin. So it's still a maximum margin approach, but it includes slack variables, which allows for overlapping classes. It also includes kernel, so we implicitly map the data to a higher dimension and then perform the maximum margin classifier in that higher dimension. But when we solve the dual, we see that we only need the kernels. We don't need the mapping at all. So the dual includes kernels so that we can learn nonlinear decision boundaries in the original space. We're still learning a linear classifier in the higher dimensional mapped space, but when we look at what the decision is in the original space, we get nonlinear decision boundaries. And so that's what makes the full-fledged, quote-unquote, full-fledged SVM so much more versatile and useful. And that's where kernels become very useful. In practice, there are many software packages, so we aren't going to discuss the actual algorithm for maximizing the dual over alpha, but there are many software packages that are available. In practice, we also need to choose a kernel function, which if we choose the RBF, means we have to choose a kernel width, which says it gives a definition of proximity in the original space. So that's an important parameter. And the way that we can do that is using cross-validation. So we can cross-validate for lambda, which is the penalty on the slack, and also cross-validate for the kernel width if we choose to use the RBF kernel, which is the most popular kernel.